Yes.
Okay. Basically, today I'm discussing about the vector control as well as director control of induction machines. Why I'm saying induction machine is, means when you are discussing the drives, we are having PMSM drive, induction motor drive, as well as different drives we are having. Basically, if you take a machine where you can call it as a both motor as well as generator. But in the case of permanent magnet synchronous motor, we cannot take a single machine. We have to have a special motor. Means you have to go for special construction for your motor as well as generator. In the case of induction machine, we'll take the same machine. We can operate it as both motor as well as generator. That's why I have taken the topic as induction machine. Means the same control methods which we are using for motor, which are applicable to generator also. Maybe the control parameters or the control parameters will be different, but method is same. Either it is vector control, director control. The controlling method is same, but the parameters what we are controlling will be different. I'm discussing today about vector control, speed sensorless control, and director control. Means vector control related to basically our main concern or main discussion point is electrical vehicles. Means in the electrical vehicle, basically, means if you take the structure of a electrical vehicle, our main part is your electric motor, which converts your electrical energy into mechanical energy and supplies to the wheels for its rotation. And our main concern is electric motor, and there are different machines or your motors we are having. Basically, your machines are classified as AC machines as well as DC machines. In the AC, we are having asynchronous as well as synchronous machines. Our main concern is our main topic is here induction machine, where we are in the induction machine. We can have multi-phase machines, where for 3-phase machine, 5-phase machine, 6-phase machine, whatever it is. Our rotor construction, depending upon the rotor construction or induction machine, is basically classified into 2 types. One is your wound rotor induction motor or slip ring induction motor, and second one is squirrel cage induction motor. We all know the difference. Means depending upon the rotor construction, in the case of squirrel cage induction motor, what happens? We are short circuiting the rotor circuit, and what we are doing? We are supplying to the stator terminals. Whereas in the case of the wound rotor or slip ring induction motor, we are supplying both for stator as well as rotor. Whereas in the case of a single phase machine, we are having capacitor as well as shaded pole types. Coming to the point of electrical vehicles, where means the contemporary machines are, one is your synchronous machine, where in the synchronous machine that we are having brushless DC machine, switched reluctance machine, synchronous reluctance machines. Basically all this means permanent magnet, where we are using the permanent magnets in the rotor structure. Means why we are specifically going for induction machine, means even though we are having the means synchronous machines where we are using the permanent magnet, why we are only stressing means why we are only stressing on the induction machine. One means basic point is, if you see the induction machine and if you compare both induction machine and synchronous machine, the point here is the cost is less and it is a very simple machine. Means construction point of view, it is very simple to construct and maintenance free. Whereas in the case of a synchronous machine, here we are having the permanent magnets, where there is a chance of means wear and tear of permanent magnet. That is not possible in the case of the induction machine. That's why we are going for the induction machine. Basically, for means if you want to go for higher cost, we can go for synchronous machines or permanent magnet synchronous machines, your stepper, your BLDC machine. But if you are going for a medium cost or low cost, generally we will use induction machine. That is the advantage of the induction motors. And apart from this, we all know DC, where we are having the shunt, series and compound motors. But we are not discussing about the means. Our main concern is permanent magnet synchronous motors as well as induction motors. Basically, even though it is an electric vehicle, but ultimately it is a drive system, where we all know the a basic drive system, where we what are the main parts of the drive system. It contains the power source, a power controller which converts different forms of supplies, means AC to DC, DC to AC, means variable DC to constant DC. We are having different power controllers, and we'll have the motor, and depending upon the load, we'll select the motor. For our case, we are selecting induction motor. And here also, if you are selecting the induction motor, even though we are discussing the electrical vehicle, but the same induction motor, I already told you, induction motor can be used as both motor as generator. But in the drive point of view, means the same motor, when we are using the motor as well as generator, what happens is the same motor we are using, the power flow will be reverse. We all know this diagram, where you will have the power source, power controller, motor, and your load. Apart from this, you will have an extra part, your controlling part. But this is the basic block diagram of an electric drive system. In the case of electric drive system, basically we'll discuss only about the motor. But if it is a generator, how your drive will be there? Basically, this is when we are using generator. Basically, we will use induction generator in the case of the nowadays we are using in the case of wind energy systems, where in the case of wind energy system, we can use squirrel cage induction generator as well as doubly faded induction generator. But ultimately, it is also a drive system, where initially, if it is a motor, you will have a electrical power supply, which ultimately provides you the mechanical, means which will do you the mechanical work. Whereas in the case of a induction generator, when we are using in the as a wind energy system, what happens is we are providing the mechanical input. Our mechanical input will be from the initially, if it is a wind energy system, what happens? We'll have a wind which converts, wind is converted, kinetic energy of the wind will be converted to the mechanical energy. That mechanical energy will be input to the motor. That mechanical input will be again converted to the electrical output. There also, what happens is we'll have all the your controller part. You will have the power electronic converter, you will have the control system, and ultimately you will have your local load or your grid. Means the power flow is reverse. The same drive system or the same induction motor, induction machine we are using, the power flow will be reversed in the case of the motor as well as the generator. We all know basically why we are going for the AC drives. AC drive means, even though I am calling it as AC drive, means almost all 70% of our industrial drives are induction motor drives. The advantage of the induction motor is it is lighter in weight, lesser maintenance. For the same cost or for the same rating, the cost of the induction machine is less. That's why AC motors are less expensive compared to the DC motors. And you can use your induction machine anywhere. Means depending upon the requirement, you can use in the hazardous areas, and you can go for the Navy application, naval applications. Everywhere we can use. The disadvantage of AC drives is when we are comparing with the DC drives, where when we are comparing the induction motor with the separately excited DC motor, already yesterday SP Singh sir has covered the DC drives. Basically means your induction motor, which is popular now, is because of the its speed control ability. But earlier what happens is we cannot use the induction motor for variable speed drive applications, because induction motor cannot be used for the variable speed. It is only used for constant drive applications. Without the power electronic converters, we cannot use induction motor for variable speed drives applications. With the help of the power electronic converters, where you can control with the help of the inverter, we can go for the variable speed drive applications. The same principle of, that's what yesterday I have discussed, the same principle of separately excited DC motor, which we'll discuss later, means how vector control has developed. Means that is the advantage of induction motor. With the help of the vector control, we are using, means everywhere in the industrial drive applications. Later on, we are having direct torque control, predictive torque control, means these are the later modifications or vertical technological developments which are developed, but the main part is we are taken the induction machine from the, means controlling part, the main controlling is taken from the separately excited DC machine, where we are having the decoupled control of torque as well as flux. The same principle we have taken and we have controlled, we have used for the vector control. That we will discuss later, how we are controlling the torque as well as the flux by using the inverter in the case of a induction motor drive. But in the case, if we are going for the, basically why we are using induction motor in the electric vehicle applications, because basically when we are using the electrical vehicles, we are having different electric vehicles, but if you see, as per our Indian conditions, our road conditions will not be very good. When there is a road condition is not good, then what happens is you have to select the machine such that which will be used for any road conditions. Then what happens is with the construction as well as the principle of induction machine, which allows the variable speed as well as torque ranges. Variable means higher speed as well as torque ranges, which will be helpful when we are using in the case of the electric drive applications due to the poor road conditions, as well as basically when we want to go for hilly areas where you require higher torque, means your induction machine with lesser cost, we are preferring the induction motor which is having very lesser cost. This diagram we have already discussed. Basically the structure of your electric vehicles, you'll have the inverter, the same means here also basically in the case of an inverter, the variable speed drive application which is possible with the help of the inverter. But when in the case of a, what happens is, if you see the basic block diagram of a drive system, where what we are having, we'll have the power source. In the case of electric vehicle, what happens is here we are feeding the machine with the help of a battery. Means we'll, with the help of the battery, whatever the supply required for your machine to run, that is provided by your battery, which is a DC supply. We are converting the DC with the help of DC to DC with the help of the bidirectional DC-DC converter, and that will be input to your inverter, a PWM inverter, which will provide the supply to the your induction motor, ultimately which runs the your electrical vehicle. This is the actually drive system in the case of a electric vehicle. Before going to the vector control, basically we have to know how we are controlling, means how we are modeling the machine. In order to control the machine, basically vector control, direct torque control, or VBF control, or these are the speed control methods. Before discussing the speed control methods, means any machine or any industrial applications, means directly we cannot take the machine without analyzing. Before going for the analyzing, what you have to know, we have to know the internal structure of the physical machine. The internal structure of the physical machine means how we are modeling the machines, means what are the different equations involved in the mathematical modeling of the induction machine. Basically, in order to model the induction machine, initially what we'll do is, your induction machine is a two-phase machine, means it is a three-phase machine, but when we are using for the vector control, what you will do is, we'll analyze the machine in two-phase manner. Means your three-phase machine is, your three phases are A, B and C. But when we are using for the vector control, what happens is your total mathematical equation involved are two phases, that is direct axis as well as quadrature axis. When the total system is in the controlling is in the two phases, what happens is we have to, even though we are modeling the machine in three phase, but what we will do is in the mathematical modeling to simplify the analysis, what we are doing is we'll start with the two phase and we'll convert that mathematical equations from the two phase to three phase transformation. And what you will do is for what you call mathematical analysis, as our machine is used in the all industrial applications, we are having the different reference frames. Depending upon the applications, we can use different, means stationary reference frame, means the same machine. What we will do, we can analyze with the stationary reference frame, synchronous reference frame, as well as rotor reference frame. We'll see. Means I'm not discussing the in-depth mathematical modeling. What we're doing is we'll take the three-phase voltages VA, VB, and VC, and we'll convert that VA, VB, VC into two-phase, that is VDS as well as VQS. In the case of a synchronous reference frame, what happens is your omega c, the speed at which your machine is rotating, omega c is equal to omega s. If your omega c is 0, you can call it as a stationary reference frame. If your omega c is equal to omega r, that is your rotor reference frame. Basically, we'll analyze we'll do the mathematical modeling in arbitrary reference frame. Means we'll not take any reference frame. We'll assume that your machine is rotating at certain speed, and we'll do the mathematical analysis, and then depending upon the requirement, what we'll do is we can go for synchronous reference frame, that is taking omega c is equal to omega s. Then your machine will be rotating at synchronous speed and your frame of reference will be synchronous frame. And omega c is equal to omega rotor reference frame, and omega c is equal to 0, it is stationary reference frame. This is the final mathematical expression of your induction machine. Basically, if you take the physical induction machine, you will have stator windings as well as rotor windings. The same means you will have the stator resistance, your rotor resistance, RS is your stator resistance, LS will be your stator inductance. Similarly, you will have the rotor resistance as well as rotor, means you will have the stator windings, which will have both stator resistance as well as stator inductance. Rotor windings will have rotor resistance as well as rotor inductance. Means based on the physical structure of the machine, means you will have the mathematical modeling. These are the equivalent circuit at different reference frame. Means synchronous reference frame where omega c is equal to omega s. Stationary reference frame, your omega c is 0. That's why you don't have this term omega g. Rotor this is in the arbitrary reference frame in dq axis. Means whatever the equation we have taken, this one, this is the final mathematical equivalent circuit. This one. Whatever the machine means, ultimately if you are taking the machine and we have to first, in order to use for the industrial dire applications, what you will do is first you will simulate your machine. Means once your model, whatever the model we are taking, whatever the model we are using, then first what you will do is first you will simulate your total model and you will test in the simulation. And these are the induction machine parameters for your MATLAB simulation. MATLAB simulation of induction motor. This is the open, means just what I have taken is I have taken the induction motor. with the help of the mathematical equations, whatever we have taken, we have written the mathematical equation in the MATLAB simulation, and for that machine, what we'll do is we'll provide the a 2-level inverter as well as a 3-level inverter. The load will be your induction motor, and we'll see the what are the speed, how your speed will be there, your current as well as line to line voltages for a 2-level as well as 3-level inverter as a induction motor as a load. A simple open loop induction motor drive without control, means without control system. Next one is we have taken the induction, means we have simulated the induction machine. Next, these different speed control methods. One is scalar control, vector control, and direct R control. Scalar control, where we all know we are only varying the magnitude of voltage as well as the ratio of voltage and frequency is varied to control the speed of the machine. What are the disadvantages of scalar control are when we are only controlling the magnitude, your speed response whatever will be very sluggish. The dynamic response of the system will be poor. That's why we have gone for the vector control. In the case of the vector control, this is the block diagram of V by F control, where only we are varying the magnitude of the voltage, means the ratio of the voltage as well as frequency. By varying the both voltage as well as frequency at a certain ratio, we are controlling the speed of the machine. The disadvantages I already told you, it is speed, dynamic response of the system will be poor, but you can go for higher speed ranges, lower starting current requirement. Next one is vector control. What is vector control and why we are going for the vector control? The reason is, in the case of a V by F control, we are not having the high dynamic performance. Dynamic in the sense, if a drive or if a machine is to be operated in the industrial applications. If you are using any motor in the industrial drive applications, what happens is you will have the different operating conditions. What are the different operating conditions? Initially, you have to start the machine from the 0 level to certain speed. Either it may be your base speed or half of the base speed, from 0 to 1200 RPM or 1500 RPM. Then I will change my speed from 1200 RPM to 1500 RPM. Later on, I will change my torque. Initially, it is at no load. Then what happens is your load will be increased. When we are increasing the load, and for some time, what we'll do is we'll decrease the load and we'll operate it as a no load. And for some application, what happens is we'll operate the machine in reverse direction. Means these are the different operations of the industrial drives. Then what happens is, if when we are using the scalar control, what happens is the response of the system will not be very fast. Means, for suppose I am changing from 1200 RPM to 1500 RPM, from 1500 RPM to minus 1500 RPM, what happens is your machine or your drive system has to cope up with the changes in the set speed. That is not possible with the V by F control. That's why people have gone for the vector control. In the case of the vector control, the main objective of the vector control is, I already told you, vector control is developed on the principle of separately excited DC machine control, where in the case of a separately excited DC machine, what happens is we'll have the independent control of both torque as well as flux. There will be natural decoupling of torque and flux. What happens is, if there is a natural decoupling, if you are controlling the torque, your flux will not be affected. If you are controlling the flux, your torque will not be affected. That is not possible naturally in the case of a induction motor. Then once we are having the different power electronic devices. With the help of the power electronics devices, what happens is we are using the inverter. When we are having the inverter as a power electronic converter, which converts your DC to variable AC, variable voltage and variable frequency AC supply. Your inverter provides variable voltage as well as variable frequency output. When it is that variable voltage and variable frequency output is provided to the induction motor, with the help of that variable voltage and variable frequency, what happens is we can control the induction motor independently, both for torque as well as flux. That's why by using a digital controller, either your digital controller, maybe your microprocessor, DSP, RTLab, and DSpace, whatever may be the digital controller we are taking, with the help of the digital controller and power electronic converter, the induction machine, which is very easily available and cheapest of all the machines, we can use in the industrial drive applications. The principle is we need to go for higher dynamic performance and at any variable speed drives, for any variable speed applications. Depending upon the how we are, means that is possible in the case of an induction DC machine. What happens is there is a natural decoupling, whereas in the case of the induction machine, this natural decoupling will not be possible. If you see this one, I am splitting the ID. I am taking this in the case of induction motor. What happens is I will take the stator current component IS and I'll split my stator current component into two components. One is quadrature axis component and second one is direct axis component. Similarly, in the case of a separately excited DC motor, what happens is I have field current as well as armature current, IF as well as IA. This IF as well as IF and IA are similar to in the vector control. IDS of an induction motor means direct axis current of induction motor is equal to field current of the DC motor. Quadrature axis current of the induction motor is equivalent to armature current of the DC motor. But in the case of the DC motor, what happens is this one, IF and IR both are 90 degrees apart. Whereas in the case of the induction motor, this IDS and IQS will not be 90 degrees. In order to maintain this 90 degrees between the direct axis as well as quadrature axis, we'll have a angle known as field angle. Theta means that is denoted as theta F. Theta F is the field angle which is maintained 90 degrees, means artificially we are maintaining in the case of a induction motor, whereas in the case of a DC motor it is natural decoupling with the construction, that is with the help of the commutator. In the DC motor you will have a natural decoupling of field current as well as armature current, whereas in the case of an induction motor that is not possible. In order to maintain artificially the 90 degrees angle between the field current means IQS as well as IDS, you will have the angle between your IQS and IDS will be theta F. Depending upon how you are obtaining this theta F. Theta F is the field angle. Depending upon how you are obtaining that field angle, the vector control. Vector control is classified into two types. One is direct vector control and second one is indirect vector control. Means depending upon how you are obtaining the theta F, the field angle, vector control is classified into two types, direct vector control and indirect vector control. If theta F is obtained by using the voltages, currents and flux of the induction motor, it is known as direct vector control. If theta F is calculated by using the voltage, current and flux. It is known as direct vector control. And if theta f, the field angle, is obtained or calculated by using the slip speed, then it is indirect vector control. If it is obtained by using the slip speed, it is indirect vector control. If it is obtained by using voltage and current, it is direct vector control. Means that is your theta f will be field angle, it is equal to theta r plus theta sl. Theta r is the rotor angle, theta sl is the slip angle. Here what we are doing is we are controlling the both torque as well as flux independently by using the if is the field current, it is the torque current. T is proportional to lambda r into it. Whereas in the case of a separately excited DC motor, it is torque is proportional to if into Ia. Field current, it is proportional to phi into If. Phi will be If, flux will be If, and Ia will be the armature current. Similarly, in the case of the induction motor, torque is proportional to lambda r into it. This lambda r will be equivalent to If into ITF. If is the field current. The field current is nothing but your direct axis current. Field current is direct axis current, IDS, and IQS is the torque current, that is IQS, quadrature axis current. This is the phasor diagram of the vector control of the induction motor. Even though it looks little complicated, but it is looking complicated because we have taken different reference frames, stationary reference frame and rotor reference frame. But you see the basic principle what I have explained, it is very simple. What I am doing is I am taking, you see this one. This is your stator current component IS. This is the stator current component IS. What I am doing is I am splitting the stator current components into IDS as well as IQS. This is IQS as well as IDS. Stator current component is split into IQS as IDS. This IQS as well as IDS means whatever the vector control we are discussing, here it will be rotor flux reference, means you can have different reference values. I can go for rotor flux reference, means whatever the reference value we are providing, that will be either it will be rotor flux reference, either we can go for the stator flux reference, that is lambda s, or we can go for the voltage, stator voltage reference frame. This one is rotor flux reference vector control, where I am taking the rotor flux as the reference value, and I am splitting the stator current component into two parts, that is IQS as well as IDS. This IQS is equivalent to, IQS is equal to torque current, which will controls the torque of the machine. IQS is equivalent to IT, which controls the torque of the machine, and IDS is equivalent to IF, that is field current. One is torque current IT and second one is the field current IF, which controls the flux. This is the main diagram, where we are taking the stator current component and splitting the stator current component into two axis. One is quadrature axis and second one is direct axis. This one is this is one a simple reference without any reference frame. For suppose I am going for the arbitrary reference frame, where I am denoting it as E. Then I am taking the stator current, the same stator current component, and splitting into arbitrary reference component by using the arbitrary reference frame, that is I am splitting into quadrature axis and direct axis. For suppose I want to go for the rotor reference frame, then same splitting I can go for the, I will take the stator current component IS and will go split like this. depending upon the our requirement or applications, whatever the means. That's when we are, if you see the mathematical modeling or MATLAB simulation of a asynchronous machine in the MATLAB, what happens is you will have a asynchronous machine, and what happens is if you go to the inside, what happens is you will have the parameters, and you can select the different reference frame. You can go for rotor reference frame, stationary reference frame, and synchronous reference frame. Okay, this block diagram looks means little complicated, but means the same when we are physically, if you want to simulate your own induction motor model, then what you will do, you will select your own reference frame. I will not go for, means I want to go for only synchronous reference frame. Then I will take this one only. But in the MATLAB or means physically, means if you want to use, means you can simulate your own, and you can use different what you call machine modeling softwares, and you can design your own machine by using different reference frame. Okay, this is how, means the principle is very simple. In order to control like a separately excited DC machine, the stator current component of a induction motor, where the stator current component, we are splitting into two axes. One is two components, quadrature axis as well as direct axis. Quadrature axis component controls the torque, which is indirectly controls the speed, and direct axis components controls the flux. That is the principle. This theta f, how we are obtaining, this is the theta f, how we are obtaining will defines the types of the vector control. These are the, whatever the mathematical modeling we have taken, mathematical equations we have taken from the mathematical equations of the induction motor. If it is a squirrel cage induction motor, what happens is, if it is a squirrel cage induction motor, this one, you see this term, voltage terms, VQS and VDS. Whereas I have taken VQR, this will be VQR and VDR. This VQR and VDR will be 0 in the case of a squirrel cage induction motor. In the case of a squirrel cage induction motor, it is 0 because we are short circuiting the rotor terminals. We are not providing the supply to the rotor terminals. But in the case of a phase wound induction motor or slip ring induction motor, I will write here that is VQS as well as VDS. VDS as well as VQS. You will have these terms. VQS means same for motor as well as generator. If it is a generator also, we will do the analysis, because we are not our rotor circuit is short circuited. Then we don't have the rotor voltages, VDR and VQR. For same for both motor as well as generator in the case of a squirrel cage induction generator, whereas in the case of a doubly faded induction generator, you will have the rotor terms. These are the mathematical equations, flux equation. Ultimately, what you will do is you will find out that this is the field current component, and you will have the torque component and speed component. Finally, you are obtaining the, if it is a indirect vector control, and I am taking the rotor flux as a reference. I already told you, depending upon the reference value, depending upon the, if I am taking rotor flux as a reference, it is rotor flux based indirect vector control. Rotor flux reference based indirect vector control. Whereas in the indirect vector control, how we are means controlling the machine is, what you are doing, we will have the omega r reference. This will be your reference value. It may be, your speed may be changing. Either it may be 1000 RPM, 2000 RPM or 3000 RPM, depending upon the requirement of the drive, or depending upon the industrial requirements, we will have the reference speed this reference speed will be compared with the actual machine speed. Reference speed will be compared with the, I'm taking the induction motor, and by using the takeout generator or speed sensor, I will sense the speed and I will compare that speed with the actual speed, and will provide, I'm comparing the actual speed with the reference speed. This error value is provided to the PI controller. This error will be provided to the PI controller. In the case of indirect vector control, or it may be a direct vector control. What is the difference here? Only this one. This part will be different because ultimately this theta calculation, theta will is nothing but this theta will be your theta f. If I am calculating the theta by using the slip, it will be indirect vector control. For suppose I am calculating this theta, what happens is by using the voltages and currents, it will be direct vector control. Why this theta f is important? Because why this theta f is important? Because you forget about all these controllers. Ultimately, what you are doing is, in the case of a vector control, what you are doing is we are transforming the quantities. The transformation of the quantities, you see, I am sensing the voltage as well as current. I have not shown the voltage sensing here, just I have shown the current. I am sensing the current IAS, IBS. In the, if I'm assuming it as a balanced supply where IAS plus IBS plus ICS will be 0. Then what I will do is I will take, what I am doing ultimately, I am reducing one sensor, current sensor IC. What I am doing is IC is equal to minus of IA plus IB. Then one sensor is reduced, that IA, IB and IC I am transforming into DQ quantities. This DQ transformation is done with the help of this theta f. If your theta f is calculated from the slip, it is indirect vector control, and your theta f is calculated from the voltages and currents and flux, it will be direct vector control. Means your total vector control, when we are comparing the vector control with director control, what happens is, a director control, you will have lesser number of transformations. Transformation in the sense, here in the case of vector control, what we are having, we are taking a three-phase, any machine, any physical machine, any industrial drive, what happens, you will have a three-phase supply. We don't have a two-phase AC supply. Either we will have a single phase or three-phase power supply. For suppose I am to use three-phase induction motor, because I can go for higher power levels. If I am using a three-phase induction motor, but my, you see, my analysis or my controlling is in two-phase only. Then what I have to do is, we have to change the three-phase quantities into two-phase quantities. These three-phase quantities are transformed to two-phase quantities with the help of the theta f. Then the theta f reflects the ultimately your transformation. This transformation is, what I am doing is, the stator current component, what I have taken IS, I am splitting into IDS and IQS. Here one is, you will have the speed controller, and second one is your current controller, or what you call torque control. This speed controller is nothing but your current controller, and second one is speed controller is your torque controller, and second one is you will have the flux controller. Initially, the first controller will be your speed controller, where I am obtaining the reference. This is the reference speed. By using this reference speed, what I am doing is, I am obtaining the reference current. By using the reference rotor flux, I am obtaining the reference d-axis component, current component. By using the rotor speed, I am obtaining the reference q-axis current. I am comparing the d-axis component as well as q-axis component reference values with the actual components. These actual components are obtained by using the theta f. These actual components are obtained by using the transformation by using the theta f. When we are having this theta f and theta, means IDS and IQS, by using the flux controller. You will have a flux controller because your flux will be your reference value, and I'll have a torque controller by using the your reference speed, where I will obtain the what you call voltages, reference voltages, VDS and VQS. Then what I have to do is, ultimately we have discussed earlier, whatever the possibility of variable speed drive application of induction motor is possible only due to the inverter. This inverter, for this inverter, what we have to do, we have to provide the gate pulses. In order to provide the gate pulses, I have to use either sinusoidal PWM method or space vector modulation method. Here I am using the space vector modulation method, where I am transforming the DQ quantities into again reference voltages, VA star, VB star and VC star. For suppose if I want to use the sinusoidal PWM, for a sinusoidal PWM, what happens is, I have to compare the sine wave reference, I have to compare the sine wave with the carrier wave. The sine wave, whatever we are using, that is obtained by using this VA star, VA, VB and VC. This is your reference voltages. These reference voltages is obtained from the your controllers, that is your PI controller. I will compare this reference value with the carrier wave, a triangular carrier wave, which will provide the gate pulses. Or suppose if it is a inverter, a three-phase inverter, two-level inverter, what happens? I will have a 6 switches, 1, 3 and 5, 4, 6, 2. Then what I will do is, I will obtain the gate pulse by using VA star. For upper switch, I have the 3 legs, 1, 2, 3. By using the VA star, I will obtain the gate pulse for the switch 1. For VB, I will obtain gate pulse for 3 as well as similarly for 5. If I am knotting the first one, I will obtain the gate pulse for 4. If I am using the NOT gate for 3, I will obtain the 6. And if I am knotting the 5, I will obtain the gate pulse for 2. Like this, what you are doing is, we are closed looply controlling the speed of the machine with the help of the inverter. Ultimately, how we are controlling means, we will have the gate pulse. This gate pulse is obtained by the reference values. Either it may be the space vector modulation or sinusoidal PWM. This reference value act as this will be the main part which will provide you the gate pulse. If your reference value, what we are obtaining, will be correct, then what happens? We will compare with the carrier wave, then we will obtain the gate pulse. Whatever the reference we are obtaining here, it is not accurate. This is dependent. This reference value is dependent upon this PI controllers. Whatever the tuning of the PI controller is, your KPKI is good, then what happens? Ultimately, your speed will be, means your response of this PI controller will be good. Once your PI controller response is good, which will provide you the VA star, VB star and VC star, which again this will be the main part for providing the gate pulses to the inverter. This is how, with the help of the inverter, what we are doing, this inverter is providing the input to the induction motor, which we are controlling the induction motor by using the vector control, where by using we are splitting ultimately what we are doing is, we are comparing the quadrature axis component and direct axis component. This direct axis component I already told you, which is ultimately this will be your flux controller. It is your flux controller. Then what happens is, it will controls the IDS, controls the flux. This will be your torque controller, which will controls the torque. IQS is used to control the torque and IDS is used to control the flux. For suppose either means the same vector control, I am not using the means either I can go for current regulated as well as voltage regulated. For suppose my reference values are currents. For suppose my reference values are currents, then I will obtain the values of IA, IB and IC. That those will be the reference values compared with the carrier wave in the case of a sinusoidal PWM. Current regulated vector control where the output of the your PI controller will be in terms of your current. IDS is compared with the quadrature axis. Reference values of IDS and IQS will be compared with the your actual values, and this will provide you the, I will have only if it is a current regulated, I don't have this PI controller. I will obtain the IDS and IQS. I will transform into IA, IB and IC. That will be used as a reference values to obtain the gate pulse. Then you call it as a current regulated vector control. Why I am discussing this current regulated vector control is, if you are going for direct vector control, in the case of a direct vector control, sorry, your director control, you cannot go for current regulation. Current regulation, you cannot use current regulation. Means the current source inverter, basically when we are using the direct electric drives, when we are discussing the electric drives, means you will have a CSI as well as VSI. Director control is not used for the CSI. That's why, means I want to tell that in the case of a director control, we are only using the voltage source inverter. We are not using the current source inverter. This is how you are controlling the induction motor, means a independent control of both torque as well as flux by using the your direct axis as well as quadrature axis with the help of the inverter, variable voltage and variable frequency inverter by using any PWM scheme. Either it may be your sinusoidal PWM or space vector modulation. Means your ultimately this control means performance depending upon SVM as well as sinusoidal PWM will be different. If you simulate by using this one, these are the outputs. I can replace, whatever I have discussed here, it is for a 2-level inverter. I can replace my 2-level inverter with 3-level, 5-level, means depending upon the whatever ranges of power ranges. If you are going for higher power applications or medium power applications, I will change my 2-level inverter with the 3-level inverter as well as 5-level inverters. Means I have simulated for diode clamped, means 2-level voltage source inverter as well as a diode clamped multi-level inverter. Next one is, means we have discussed about the vector control. In the case of the vector control, ultimately what we are doing is we are using this one. If you see this block diagram, this is the speed sensor. The speed sensor, whatever we are using, without the speed sensor, we can control the speed of the machine. If you are controlling the speed of the machine without using the speed sensor, you call it as a speed sensorless vector control. Speed sensorless means we are eliminating the sensor. If you are eliminating the sensor, is the advantage is your cost is reduced, and second one is you will have some applications. You will have some applications where we cannot go for the sensors, means some hazardous applications and naval applications. Fixing means if it is a small laboratory type of machine where what happens is fixing of rotor sensor for the rotor shaft is easy, but for huge machines where, for suppose if my shaft means my sensor is not working properly and am I using my motor in the naval applications, then what happens is I cannot replace my sensor frequently. Then what we'll do is, means at that applications during those places, what we'll do is we'll control the speed of the machine but without the speed sensor. Then you call it as a speed sensorless vector control. One is advantage of speed sensor is reliability is more, cost reduced. There are different speed estimate, you call it as a speed sensorless techniques or speed observer, speed estimation techniques, whatever it is, there are different methods. That is spectral analysis is, this is dependent upon the means mathematical and means what you call, you will inject the high frequency signal into the machine, then it is the spectral analysis. And the fundamental, we will take the fundamental induction machine, and by using the induction machine equations only, what you will do is we'll control the speed without the sensor. Those methods are speed observer. These speed observers are extended Kalman filter, uncentered Kalman filter, Leonberg observer, adaptive speed observer, and sliding mode observer. Second one is model reference adaptive system. The MRAS is model reference adaptive system. Again, it is classified into different types: rotor flux based, back EMF based, reactive power based, stator current, and rotor current based. Means depending upon where we are using. If it is using in terms of motor, as well as in the case of a generator, your speed estimation methods will be different. Either you can go for artificial intelligence techniques, fuzzy logic, neural network, ANFIS, genetic algorithms, and open loop estimators. I am discussing today about the model referensive adaptive system, where rotor flux based model referensive adaptive system. In terms of electric vehicles, means why your speed sensor less application is used. In the case of a, if I am having electric vehicle, I am not using the sensor. The advantage of not using the sensor is already told you, means the cost is reduced and reliability is more. And the other advantage of the machine is, if I am using a speed, if I am using without, I am controlling the speed of the drive without speed sensor. In the case of a electric vehicle, what happens is electric vehicle contains different components. You will have a not only your drive system, which not only the motor, you will have your AC, all your lighting systems, everything will be there. For suppose there is any fault in the system, if there is any fault in the system, what happens is ultimately your motor will not work, or if there is any power short circuit in the system, what happens, you don't have the, if there is any power failure, then your machine will not work. During those applications, what happens is, even though during the power failure, if you are going for the speed sensorless control, what happens is, the advantage of the machine is you can control the speed of the machine. When we are controlling the speed of the machine, if it is a power failure, what happens is you cannot go for higher speeds. Got the point? If there is any power failure, what happens is, my machine in my vehicle is running, but the speed of operation is not same as the earlier one. Then what happens is, if any machine, what we are taking means the, what you call, if there is any power failure in the system, and during the conditions also we are operating the vehicle, we call it as a limp home period. This limp home period is nothing but there is a power failure in the system, and we are operating the, means ultimately we have to reach safely to the home. During those critical conditions, if I am controlling the drive, it is very good. Thus, during that critical operations, what happens is, if I am using the speed sensorless technique, I can control the speed. But if I am controlling the speed of the drive at the lower speeds with the help of the speed sensorless techniques, what happens is, my machine parameters will affect the performance of the speed control. We'll see later how it affects the performance of the drive during the limp home period. But initially, we are discussing about the model referensive adaptive system, where it is a very popular speed sensorless technique where you will have a reference model, a adaptive model. Reference model is actually your machine model, your induction motor model. You will have the voltage equations of the induction motor. You will have a from the reference model as well as the your adaptive model. We are obtaining a component, means depending upon this is epsilon. This epsilon is nothing but the error value. This error value, for suppose if it is a, means depending upon how you are obtaining this epsilon omega, your model reference to adaptive system. This epsilon omega is known as a speed tuning signal. This how you are obtaining this speed tuning signal. For suppose I am obtaining this speed tuning signal by using the rotor flux components. Already I have taken the rotor flux as a reference. If I am obtaining by using this, means one is d-axis rotor flux component and second one is q-axis rotor flux component, which is obtained by using the reference model. This is my actual rotor flux of the machine. I am comparing this actual rotor flux of the machine with the estimated. Adaptive model gives the estimated model. Estimation is nothing but what happens is I have my machine is rotating at certain speed, means I have the reference speed. Without the speed sensor, what happens? I will get the actual value of the speed by using the speed sensor. But for suppose if we don't have any sensor, then what we will do is we'll estimate the speed value. That speed value means estimated initially. First we will estimate the rotor flux. In the case of a rotor flux based MRS, for suppose my flux means epsilon omega is obtained by using the back EMF, that is ED as well as EQ. Back EMF, ED and EQ, then I call it as the back EMF based MRS. If epsilon omega is obtained by using the reactive power, QD as well as QDS as well as QS as well as QDS. Then I call it as a reactive power based MRS. For suppose in the case of a generator, what happens is I will use rotor current components. In the case when we are discussing the in vector control, in the case of induction motor, your main component is, means I am splitting the stator current component into IDS and IQS. In the case of a generator, I will split my rotor current component IR into IDR as well as IQR. Means if you are splitting the, means if your epsilon omega is obtained by using the stator, means rotor current IRD and IRQ, then I call it as a rotor current based MRIS. In the model reference adaptive system, this equation, this is the actual machine equation, what we have, means mathematical equation of your induction motor. And by using those equations, what means I will find out the rotor flux component, estimated rotor flux component, and will compare with the, will multiply with the actual value as well as estimated value, and will compare with the epsilon, compare these two values, multiply product of QRD as well as psi RD as well as psi RQ, and the product of psi RQ as well as psi RD cap. Cap denotes your estimated value. Then I will obtain the epsilon omega. This epsilon omega will be provided as input to the PI controller. Either you can go for your PI controller, fuzzy logic controller, or neural network controller. Any adaptive mechanism I can use. Then I will obtain the your rotor reference, means estimated rotor speed. Here you will have the omega R cap. This is the estimated rotor speed. This I will compare this estimated rotor speed with the, what it means, I will compare this with actual rotor speed. Sorry, your reference rotor speed. Earlier what I am doing is I am comparing this with the actual rotor speed, that is which is obtained by the speed sensor. In the case of a speed sensor method, I am comparing with the actual, means estimated value. Means when my reference means the comparison is changes, whole system now works with the your estimated values, and whatever the voltage values we are obtaining the same indirect vector control method, then my VA and VB star will be now obtained with reference to the your estimated value. This is how we are controlling the speed of the machine by using the speed sensorless technique. You can go for any speed sensorless technique. These are the means reference model equation, adaptive model, mathematical equation. This is the omega r. If I am using the PI controller, means Kp as well as Ka. Epsilon omega is equal to psi QR product of and estimated value. Here product of psi dr as well as psi QR. You will get the estimated speed. This is your estimated speed. Earlier it was actual speed of the machine, which is obtained by using the speed sensor. What are the disadvantages? I already told you, means for electric vehicle applications, during the limp home period, what happens is my machine will run at very low speeds. When the machine is running at very low speeds, then what happens is means controlling will be difficult. What happens means how the performance of the machine is affected during the low speed values. If it is a model reference adaptive system, you will have an integrator. This psi dr is equal to, means P into psi dr. If you take it to the other side, it will be integral of LR by LM, integral of VDS minus. This is the voltage equation of the induction machine. Means you will have an integrator which affects the performance of the means response of the system. You will have a which introduces the delay into the system. That is a one disadvantage. Next one is, you see here we are having the stator current, stator resistance as well as stator inductance, whereas here we will have the rotor inductance. This TR is LR by RR, rotor resistance, rotor inductance by rotor resistance. Ultimately, what happens is your performance is affected by the machine parameters. Means the performance of a model reference adaptive system is sensitive to the parameter variations, because you will have the stator resistance values as well as stator resistance as well as rotor resistances, pure integrator, which delays the system performance, and ultimately what you are doing is you are using the voltage, means you are using the, even though we are not going for the speed sensorless method, but we are using the voltage sensor as well as current sensors. Then what happens is, when we are using the voltage as well as current sensors, you will have the, when there is a very low values, what happens is this voltage as well as current sensors will not provide you the accurate values. When this value is not accurate, this voltage value is not accurate, then what happens is ultimately whatever the flux we are estimating, or this will not be accurate. Then what happens is your speed response will be poor. These are the disadvantage of model reference rotor flux based model reference adaptive system. Then how can you improve the performance? One is I can replace the one, I can go for the parameter estimation. Second one is I can go for the neural networks and fuzzy logics. There are different methods. Means I can modify the this method, whatever the these equations, I can do the mathematical modification and I can obtain this rotor flux. Second one, I can modify the reference model, or I can replace this PI controller either with fuzzy logic or neural network, or I can estimate the speed values, sorry, your resistance values. These are the different methods to improve the performance. One method is I can modify this total equation, or I can estimate these values, rotor resistance as well as stator resistance, or I can go for the replacing this PI controller with the fuzzy logic controller, which provides the good speed response. Modification in the sense, this is the mathematical means LR by these equations. What I can do is I can add a component. This is nothing but means you don't go for complicated value. Simply what I am doing is I am adding this compensating voltage. Ultimately what we are doing is, if this value is accurate, means this value is good, what happens accurate, then what happens, my epsilon omega error value will be less. Then means based on this one, what I have done is I am adding a compensating voltage. My basically this voltage VDS will be less during the my limp home period. Means during the low power, low speed applications, this value will be very less. Then what I am in this, I am adding a compensating voltage to this value such that I am improving this psi dr. A compensating voltage added to both d axis as well as q axis components to improve the rotor flux. That is modified voltage model MRS. Nothing means, oh, it's a kuch nahi hai, but means if I want to tell simply, just I am adding a compensating voltage to the this term. How I am calculating this compensating voltage? By using the internal structure of the same machine equations of the induction motor. But the same reference rotor flux, whatever I have taken for the vector, indirect vector control, I am taking the reference rotor flux and using a controller, and I am using the drift as well as offset values. Basically, why I'm adding this drift as well as offset values, what happens, the integrator present, this one, what it will do is, it will provide you the DC drift. That value, taking that DC drift into consideration, I'm adding a DC, means a compensating voltage to the D axis as well as Q axis. That is what I'm doing. Just I'm adding the same equation, but what I'm doing is I'm adding the compensating voltage, that is VCP Q axis as well as D axis. This VCP is nothing but offset voltage as well as drift voltages for both D axis as well as Q axis. My adaptive model will be same, only I'm modifying the reference model. Only I'm modifying the reference model. This is the adaptive model, means whatever the adaptive mechanism, this one, this adaptive mechanism block diagram. Epsilon omega. Next one is what I'm doing is I'm replacing the, even though I'm modifying my reference model, my performance is not up to the mark. Then what I have done is I am using the fuzzy logic controller in the place of the PI controller. Just I'm replacing the means fuzzy logic. Basically, I'm replacing the PI controller with the fuzzy logic controller, where I'm providing the ultimately fuzzy logic controller is, it contains different blocks, that is fuzzification, knowledge base, inference engine, and defuzzification. Basically, what does it is? Fuzzification is nothing but you will have the input is your real value. That is your real values are converted to the your, take the other sense, it is converted to its own language, that either it may be your binary value, something like your binary, means your real values is converted to the a fuzzified values, and you'll have the rule base, that rule you'll write the rules, means according to the your application, you will write the rules. That rule is written in your knowledge base, and you will process those rules by using the inference engine. Then that ultimately this is fuzzified value. After the inference engine, what happens? You will have a fuzzified value again, but I want to use my real values. Then I will defuzzify, means transformation from real to fuzzified values, and detransformation, that defuzzification from fuzzy to real, that is fuzzification, defuzzification. This is nothing but processing as well as writing the rules of the fuzzy logic controller. Just I am replacing the PI controller with the fuzzy logic controller, where I am fuzzy, this is fuzzy PI controller. where I am using means have to means ultimately for the you have to you'll have a PI controller. Basically, your fuzzy PI controller is developed based on the based on the PI means you for suppose how you are I am writing these equations means rules is take a second order system, take a second order system, response of a second order system. In this, what does NB? NB represents the negative big. This is NB. PB represents the positive big means positive side. What is my maximum peak? Like this, I have taken. This is for the NB negative medium. This is my negative medium. Like this is my positive medium. You will have a same negative big, negative medium, negative small, positive big, positive medium, positive small, and zero errors where I don't have any error value. I'll have two error value as well as two inputs, error as well as change in error. Error as well as change in error means my error is negative big and my change in error is negative big, then my output means my output will be negative big. Or suppose my error is negative big and my negative error, change in error is negative medium, I will take it as a negative. Like this, you have to write your rules according to your requirement. Okay, means such that you will obtain your actual response of the system. Either you can use in any control system, not only in the model reference or adaptive system. Like this means you can go for the writing the rules. Next one is I have taken different conditions. What I have done is ultimately my main motive is to operate the machine at lower speeds. Higher speeds, I don't have any problem without speed sensor. But when I am using the speed sensor, when I am not using the speed sensor, and my vehicle is I am having a fault in my vehicle, and I have to go home safely, and I have to see the performance of the drive during those time. Means I'll have the different speeds. Initially, I'm starting the machine from 0 to 100 RPM. Then it is at no load condition. Then at 2 seconds, I will change my speed to 100 to 50 RPM. That at 4 seconds, I will apply the 50% of the load. At 6 seconds, I will change my speed to 50 to 100, 50 to 20 RPM, then 20 to 10 RPM, and I can go for zero speeds also. Zero speeds, basically it is used not in the case of a electric vehicle, but in the case of elevators. What happens is, even though there is no movement of the elevator, but it is what I mean, there is your machine is continuously running. During those applications, what we will do is you have to see the performance of the machine, that is during the zero speed applications. These are the different speed responses for one is conventional model reference adaptive system. Second one is modified MRIs where I am using the compensating voltage, adding the compensating voltage. Whereas third one, I am adding the modified compensating voltage, and I am replacing the PI controller with the fuzzy logic controller. This is simulation results. Means replace it the 2-level inverter, means inverter with the 3-level inverter. What is the power quality parameters? The voltage. How we are performing means experimental implementation of MRIs. For the experimental implementation, whatever the mathematical simulations we are doing, just what we are doing is we are using a digital controller where you can use for a DSP RT lab as well as DSpace processor. DSpace DS1104 processor, where I'm using. Basically, this processor is used to provide the gate pulses. Your total control, I have already told, which is dependent upon your inverter. Without inverter, we are not going for the vector control, because without the variable voltage and variable frequency converter, that independent control is not possible. That's why the gate pulses, whatever we are providing to the inverter, that is very important. That is provided with the help of your digital controller, where this will, I'm taking the, in this one, what I'm doing is, we'll have the PWM inverter. This is what you call, means this inverter, your digital controller will provide you the gate pulses. But what does it require? Means it is require the digital values, means analog. My voltages and currents means are analog values, but I am converting that with the help of the ADC, my IA, IB, IC. Okay, I have already told you I have only using only two sensors, IA plus IB is equal to minus IC, or other way, IA plus IC is equal to minus IB. These real values or analog values is converted to digital value with the help of the ADC. And second one is, I'm not using the current sensor, or no, sorry, voltage sensor, because I'm only using a DC. I'm sensing only the DC link voltage, VDC. With the help of these DC link voltages, I'm obtaining the gate pulses. I'm taking these gate pulses and I'm obtaining the VA, VB, VC. Means here, in order to reduce the cost of the system, what I'm doing is I'm reducing. Initially, I can use two voltage sensors, but again I'm going for only single voltage sensor. That is, only I'm sensing the DC link voltage, and I'm obtaining the VA, VB, and VC, that I am converting into digital value with the help of the ADC. For the reference purpose, whatever the speed value we are obtaining, that is accurate or not, I am comparing with, this is only for comparison purpose. I'm using the encoder, but actually I'm sensing using the speed sensor. We are using the speed sensorless method, but whatever the speed estimated value we are having, that value must be equal to the actual value. How can we know? Just for compare, we'll compare with the, we'll see, compare with the actual speed value with the help of this encoder, which will, means ultimately we will have a control mechanism, your control vector control here. But in order to provide the vector control, means you will have the total control mechanism with the help of this digital controller by using a, means your DSpace, and will provide you the gate pulses, which will control the speed of the machine. We'll have the actual speed of the machine, reference speed means my reference value 100 RPM. Actual speed means the speed at which my machine is running. Estimated value means the speed by using the model reference to adaptive system. Say for conventional model reference adaptive system, modified voltage model system, as well as fuzzy logic based modified MRS. These are the speed responses at different speeds. Load change, speed change 100 to 50, 50 to 20, 20 to 10, and load change at, means 50% change in the load. This is because if my estimated, means my flux, whatever the estimated flux is accurate, then what happens? My epsilon omega will be, error will be less. Once my error will be less, the input to the PI controller or fuzzy logic controller will be good, which will provide the better response. This is it, just for reference at higher speeds. What is the response of the system? Comparison. Fuzzy logic based MRS, modified voltage MRS, will provide the better response by using the multi-level inverter. Means peak overshoot as well as settling time. Next one is, I already told you, means speed performance is affected due to the change in the parameters. That is, we need to estimate the, means we have to, means when we are continuously running the machine, when we are continuously running the machine, means even though at higher speeds also, what happens is, due to the positive temperature coefficient, the resistance, your machine gets heated. Your machine gets heated is nothing but your, what happens, your machine resistance is, your stator resistance or rotor resistance is increasing as it is having the positive temperature coefficient. Even though it is, its value is increasing, then what we have to do is, we, whatever the stator resistance estimator, means we will go for online stator resistance estimation, that will not affect the model reference adaptive system. That is your stator resistance estimation, in order to first find out how the machine resistance, stator resistance is increasing. Take a indirect vector control and run the motor for 3 to 4 hours, and initially you measure your stator resistance. It will be whatever may be the machine parameters, its value will be some x. For suppose I am continuously running for 4 to 5 hours, it will be x plus delta x. If it is x plus delta x, what happens is, this value will affects the flux estimation. That is, whatever the flux value, what we are psi rd or psi rq, this will affects the this value. Once this value is affected, then what happens, your epsilon omega is not good, then this omega r cap, that is estimated rotor speed, will be changing. That's why what you will do is, this effect of this delta x must be nullified. In order to nullify this effect of delta x, we are using the neural network controller. This is the estimated resistance. Means how equation for estimated resistance, the same mathematical equations of the induction motor. By using the mathematical equations of the induction motor, we are estimating the stator resistance, and this one we are replacing with the C. Your omega, sorry, RS cap will be estimated resistance by using the neural network based stator resistance. What happens when we are using the neural network? The advantage is, it will does not, parameter variation does not affect much on the neural network. It is immune to the variation of the parameters within the system. That's why we are using the neural network based stator resistance estimator. This is the mathematical equation, neural network based mathematical equation of the, means here what we are doing is, basically we will take for estimation, we will take the actual value of the, means del t as well as t minus 1 value. That is actual value of the rotor resistance as well as the previous value, such that we will get the actual estimated value. This value represents basically whatever the equation. For suppose this equation IDS is this omega. This is dependent upon the IDS as well as IQS. IDR and IQR means we'll take the previous values as well as actual values of the this currents as well as fluxes. This is you see, if without parameter variation, what happens is, if you are not considering the stator resistance variation, what happens, due to the variation in the resistance, your speed response will not be good. That's why we'll go for the actual, means first we'll go for the speed stator resistance estimator, and next one is, by using the neural network, we are estimating the stator resistance. There are different variations in the parameters due to the variation in the speed response due to the parameter variation. Same thing we have, means the same experimental method what we have done, we are using for the stator resistance estimator also. Help in the case of a conventional MRAS, without parameter estimation, your response will be very poor. Means you ultimately you'll have a steady state error. Means your speed will not be your speed will not settle down. With two-level inverter as well as comparison with the two-level inverter as well as response of the system for two-level as well as three-level inverter. Conclusions, ultimately what we are doing is by adding the first one thing is by adding compensating voltage, we are improving the voltage term. By adding the compensating voltage, we are improving the means reference model voltage to improve the performance means of the your reference model. And second one is by replacing the PI controller with the fuzzy logic controller, your response is steady state as well as transient state response will be improved. And using the neural network based stator resistance, your means what you are doing is we are nullifying the estimation means stator variation of the stator resistance. It is robust to the variation of the parameters. The system is robust to the variation of the parameters. Next one is direct torque control. The disadvantage of vector control is already told you in the vector control obtaining the theta f is difficult and maintaining the theta f constant will be difficult. If you are maintaining theta f constant means 90 degrees, then only you can control the speed. If you are not able to do, then it will be your response will be poor. In order to maintain that, what you will do, you have to go for the coordinate transformation, that is 3-phase to 2-phase transformation and 2-phase to 3-phase transformation. In order to avoid those difficulties, we have gone for the direct torque control, where we are taking the means the reference value will be stator flux as well as the torque, means where directly earlier also we will have the controlling the torque, but here we are not controlling we are not directly controlling the torque. Here we are taking the torque as the reference value and we are controlling the speed of the machine. Torque as a reference value as well as stator flux as a reference value, where we are directly controlling the torque. Whereas in the case of indirect vector control, we are not directly controlling the torque. In order to control the torque in the case of a direct torque control, earlier we are using the what you call PI controller. Here we are going for the flux comparator as well as the torque comparator. Here we are using the hysteresis controllers. Basically, direct torque control, when we are comparing the direct torque control as well as vector control, is in the case of a direct torque control, you will have the, for suppose you take I already told you here we cannot use CSI, that is current regulated inverter, where we are only using the voltage regulated inverter or voltage source inverter. For this voltage source inverter, basically you will have the how many switching states? 8 switching states. Depending upon these switching states, that is 6 active vectors, that is S1, S2, S3, S4, S5 as well as S6. Whatever the switches, what happens is it will have a switching vectors where 2 null vectors, that is 0, 0, 0 as well as 1, 1. Remaining are 1, 0, 0, 1, 0, 1. Like this, you will have the 6 active vectors. You have to select the active vectors, means this is the switching logic. In the case of a means by using this theta s, by using here we are obtaining the, there it is theta f, here it will be theta s. Depending upon the this theta s, what happens is you will have the, you will select the vector. Basically in the, you will have the fix S1, S2, S3, like this you will have the switching vectors and you will have the variation of your flux as well as this one. What we have to do is depending upon the selection of this vector S1, S2, by changing the values, if you see here, basically you will use the comparator, flux comparator as well as the torque comparator. Means depending upon this, for suppose I will the flux comparator is a 2-level comparator where you will have the x means change in value will be, you will have the flux change in value +1 as well as -1, whereas in the case of torque comparator it will be +1, 0 as well as -1. Means depending upon the these values you will select the switching vector depending upon the, for suppose these are the different switching vectors. These are, for suppose my x lambda is +1, that is x lambda is increasing, flux is increasing. For suppose flux is increasing and torque is increasing, I will select this switching vector. For suppose my flux is increasing and there is no change in the torque, I will select this switching vector depending like this. What we will do is, in the case of a indirect means direct torque control, you will have the predetermined values. These values are means basically direct torque control is variable, means it is the disadvantage of this one is it is variable switching frequency, means there is no constant switching frequency. Your machine, your control will don't have the constant switching frequency. That is the disadvantage of the, means this is ultimately your switching will be dependent on you will have the variable switching. This depending upon these values your switching will be varying. That is the disadvantage. Means if it is in sector 1, you will select these values like this. If it is in sector 1, how your flux is varying, as well as how your torque if it is in the sector 2. Like this, what happens is you will select your switching vector such that will provide you the gate pulses. Okay, whereas in that case you will have a VA star, VB star as well as VC star. That is the actual reference values in the case of a vector control. These values, these switching values is dependent upon this change in the flux as well as xt as well as x lambda. These are obtained by using the hysteresis controller. This is how, means brief introduction of direct torque control. Thank you. Any doubts?
Hello.
Hello.
Sir, good afternoon. Sir, I have a query about scalar control. Sir, in scalar control, we are getting a slip speed from speed error. So I was searching some papers, so I'm not getting able to how this slip speed is calculated with the help of speed error.
With the help of
speed error.
You will have the equation. You will have the slip equation.
Yes, sir. I'm asking for that.
Omega SL. Yeah. You will have according to that equation. This one, no?
Yes, sir.
This one we are obtaining from the what you call your controller.
Limiter.
Yeah, that's your limiter. Ultimately, this is obtained from the controller, your PI controller, where you are limiting the what you call your slip value.
Okay, sir. So, is there any reference for that thing where I can go in detail?
You can. This is from BK Bose.
BK Bose.
You can see the BK Bose.
Okay, sir. Okay. Thank you, sir.
So, any other query from any participant? So, I feel there is no query from any participant now. So, So, on behalf of Department of Electrical Engineering, Maulana Azad National Institute of Technology, I, Dr. Ujjwal Kalla, extend hearty vote of thanks to our speaker of this session, Dr. Giribabu. Dr. Giribabu has spared his time from his very busiest schedule and delivered an excellent talk on controllers for induction motor in electric vehicle applications. Okay, and we hope that this talk would be very beneficial for all the participants working in the area of induction motor control and electric vehicle area. Okay, and so thank you, Dr. Giribabu, for delivering such an excellent talk.
Thank you, sir. Thank you.
Anytime. Thank you.
Thank you, sir.
Now we close this session, and we will be meeting again at 2:30 with the session of Dr. Ujjwal Kalla. So all the participants are requested to be on time. Thank you, and we break for lunch.